So now let's talk about other combination models. So there is others like a mixture of experts. So mixture of experts here mean to get experts classifiers specialized on certain aspects of the problem. So here the diversity is induced by the fact that our models are trained on more intensely on some subsets of the training set or the type of data we can see. And the point is to make them work in parallel, but we have a routing function that is weighting decision dynamically according to the expertise. So it's similar to weighted voting, but the weighting is not constant. It is changing every time. So we have, in fact, W not as a weight, but as a function of X that is determining the expertise for each members according to the X. And the point is to say, by reducing somehow the space correlation, let's specialize every member on differently in each region. So this will generate some kind of bias experts, but it will be negatively correlated somehow. This is what we want to look at for. We want to get them not correlated, not making the same mistakes at the same place for the same class, the same data. And with that, we want to reduce the variance and as such the error. So the routing function can be non-linear. No, it doesn't have to be a linear model. We can use, for example, multi-layer perceptron as the model for the WJ here. So this is interesting because it may reduce the bias, but we can overfit somehow with a really strong model in terms of the routing. So chances of overfitting are there. So basically, the mixture of experts will look like this. So we have each of our models that are trained with specialization. So basically, we will probably oversample some part of this, the X's coming from some part of the space to get this specialization. Can be also based on the labels or other measurements. But the point is to get some kind of expertise with different models that are not trained the same way, that have some expertise. And we have the gating function, which can be linear model or multi-layer perceptron. And in that case, we will learn to weight every decision according to what we know of the expertise of the members. So the gating can be trained on somehow the observed decisions and observed errors of each member of the mixture, each expert of the mixture. Another model that is not that different is what we call stack generalization. The idea is to make a two-stage system with at the first stage, basic classifiers working in parallel. So this is pretty much similar with mixture of experts. But the second stage here, we don't have access to the X. We are just working on the decisions of each members at the first stage. So this is what we are lying. And the point is to say, okay, with this combination function, we hope to see pattern in the decisions that will allow us to correct some cases of ambiguity in the right way, in the smart way. So basically, if all the decisions are kind of coherent, that's easy. If there are some ambiguities, the combination system will look at these ambiguities, will rely on possibly the training set and see, well, when 1 and 2 are saying something and 4 is something else, which is different, we should rely on 1 and 2 in these cases. But in some other cases, we also may rely on 4 versus 5 and 6 and so on. So we should be able to see decision patterns and be able to correct or adjust and make the final ensemble decision based on the combination system. So it is basically a standard classifier. And that's why we call this stack generalization, because we are stacking a level of many basic classifiers with another level of a standard classifier that is built upon that. And in fact, this model will learn how the basic classifiers are making mistakes, and will train, we need to train that level somehow with unseen data, because we need to split some of the training set in two. We are really like the basic training set for the base classifiers, and we need to get some kind of stage 2 training set for training the combination system to be sure that it will not be based on the same samples than the one used for level 1, stage 1. And so that should allow to estimate and correct the biases of the basic classifiers. So it looks like this. So the difference with the mixture of experts is that we don't have access to the X, we only have access to the decision of the members. The rest is kind of similar. Even though the gating is more than just a weighting, it's really just, we can have many layers of neurons, for example, in the combination function. So it goes more than just rewrite every decision. It goes into possibly making a kind of different decision according to what should be done. Another approach is cascading classifiers. So the idea is not to work in a serial manner, is to get a sequence of basic classifiers, but not getting through the sequence all the time. We are moving, in fact, from one stage to another if the classifier K has a low confidence in its classification. So basically, if we see that confidence is lower than a given threshold, we are going into the next stage. If it is higher than a given threshold, we just stop there and we assign the decision as the one to use here. So the decision is basically this thing. We are somehow having this rule here that say we will stop. We will, I would say, stop at the point where the threshold is over a given threshold. The weight is over a given threshold. So the confidence for classifier J is over a given threshold, assuming that all the other stages before were lower their corresponding threshold, which doesn't have to be the same from one stage to another. And then the ensemble decision will be basically the member at the current stage where the confidence is good enough. So the confidence Wj can correspond to the a posteriori probability of the classifier, basically. So we can use this directly. And the threshold on the confidence should be high, At the first stage, we should be super selective and pick up only and say stop only when the decisions are made with super good confidence. And we need to get well-calibrated confidences, because if not, how can we rely on it? And so the point for the training is to say, okay, we are training the first classifier with the full training set. And once the training is done, we will apply them on the classifier, and we will just keep the rejections. So the ones that are not passing the threshold for Hj, it says H1 at first. So, and then we will use the rejection, the one where the confidence is not good enough, as samples to train the next level, the next stage classifier, and so on. We are repeating this over the different levels that we want to use in our cascade. So the idea here is basically to use basic models at first. Possibly we can have different models at the different stages, and we want possibly to start with super simple, fast, inexpensive classifiers in the first levels. But as we get into samples that are not confidently classified, we can use much more complex classifiers to deal with these cases. So because these were handling the difficult cases, we need to be cautious because the number of complex cases may be kind of small compared to the number of samples at the first stage. So it looks like this. So we have these decisions made here based on a given threshold, so we have the first stage classifier, its confidence. Are we enough confident? Yeah, we stop here. Otherwise, we got the stage 2. Confidence, are we confident enough? Yes, we stopped here. No, we continue like this up to the last one, which is just based, the decision is just based on the last model once we reach the end of the cascade. And this model is particularly interesting for real-time processing. When we have to process things in real time, possibly having a stream of images, a stream of data that is coming fast, we may not be able to apply the most complex classifiers at the end of the cascade to all samples. We will be overwhelmed in terms of number of data to process. So possibly with this model, we will just keep some of them to go with the more complex classifiers, but the easiest ones will be processed with one of the first stage, which should be fast. Another approach is what we call overproduction and selection. So the idea is to build up, I would say, we can say that somehow our model of ensemble is a meta classifier, because we have this H bar here, And we see that it is in fact put into a function, a routing combination function, that is relying on every output of each models. And looking at this, we can see that basically the HI, are the features of the meta classifier, and the decision here is the meta classifier. So why not making use of something that will be slightly different, but that will support this? The idea is to say, okay, let's generate first a wide variety of candidate classifiers. So maybe let's use random subspaces, for example, and train, I would say, hundreds of models independently, only on different feature subsets, different training subsets. And the point is to say, okay, from that, we have the different candidates. Maybe some are poor, maybe some are redundant. So let's pick up a subset of these classifiers that are, I would say, good when used together for an ensemble. So the point is to make use of that. So we are overproducing a bunch of models, and then we are picking up the ones that seems the most relevant, and we can use what we call feature selection methods, which will be seen next week. But there is a good link between this, because if we are saying that we are working with a meta classifier, like we say here, each member is a feature. So we don't necessarily want to use all features. We want to use some of these features, some of these models. So if we just use an overproduce and select, we say, okay, let's generate 1,000 models, but 1,000 models is huge. It's not manageable in practice. Let's pick up maybe 25 at the end of these models. So we have 1,000 models that are overproduced, and then we will select 25 of these models. And so selecting 25 is like a feature selection problem. When we have 1,000 features with many redundancy, we don't want to keep all of them. We maybe want to keep 25 features over the 1,000 of features. So many approaches are possible, like the sequential forward selection and sequential backward selection, which will be explained next week. And we also have things like multi-objective evolutionary algorithms that can be used because they are particularly fit to this kind of combinatorial optimization problems, where we want to pick subset of something according to possibly several objectives, like here will be to maximize accuracy while minimize the number of members used.